Hey, thanks for joining me. My name is Dave, and this is the first of a series of videos that I'm going to be recording about this project that I've worked on for a few years, on and off since undergraduate, building this JavaScript software library, an adaptive Radix tree. So in this video, I want to give like an overview of the project, and I'm doing it here in the opening scene of Half-Life Alyx. I wanted to do something kind of unorthodox. So I'm releasing it under the GPL license on GitHub, and there's a write-up that goes along with this. These videos I just want to go over what an adaptive Radix tree is, what mine is like, and what you can use it for. There's a lot of cool things with it. So today we're just going to be talking about general overview of the project, though. In the future we'll get into more detail. So what is an adaptive Radix tree? So I want to start by talking about sort of what it's not. So it's not like one of these other data structures, right? Like a binary search tree, for example. I'm going to juxtapose this adaptive Radix tree concept to binary search tree, mainly because I made one beforehand, but also binary search trees are maybe a little bit more common. And so before we even talk about adaptive Radix tree, what's a binary search tree? Well, a binary search tree, the concept there is, you might want to use it to index numbers, for example. Okay, so you have nodes in this tree, and let's say you have the number. You have in each node, it'll store like one number, and then each node can have up to one or two children, right? And so let's say that that's the first number you put in the tree, and now you want to store the number 5. Well, you come in here and you realize the first node's taken, and it can have up to two children, a left and a right child. And if the number that's being inserted is less than the value of the current node, then you would put it to the left. So the 5 would go over here, right? Then let's say you have like another one that you want to insert, and let's say that it's 17. Well, then that's greater than 11, so that would go over here. Okay. You can have only up to two children, and so let's say you have another one that you want to insert. Let's say you want to insert the number 8. And that would go like over here, the right child of number 8. And you can just keep going and going and going like this. Okay, and that's the concept of a binary search tree. It's very easy to find what you're looking for, because it's the phone book algorithm, as they call it, where you just start at the root. If you're looking for, let's say, the number 8, to find it, to see if it's in the tree, you would start at the root and say, is this 8? Nope, it's 11. But 8 is less than 11, so you can go left. And you have a 5. Well, is 8 less than or greater than 5? It's greater than. So that's how you can find what you're looking for. So that's kind of the concept right behind a more traditional tree, like a binary search tree. A Radix tree doesn't store a whole key inside of each node, right? And by key, in this case, it's a number. It doesn't have to be numbers. It could be strings or some other data type, some compound data type that you store in each node. With Radix trees, you're not storing an entire key in each node, okay? With a Radix tree, it's a type of tri-data structure, which means that as you descend the tree through the branches, you're kind of indexing slices of a node, or of a key. So in a Radix tree, you'll have a root node, okay? And the root node, it indexes the first byte. Now, I'm kind of being specific here. I'm saying the first byte. Actually, there's a lot of different types of tries, and you can try to, there are different ones. It doesn't have to be a byte at a time for each node. It could be just a bit or a few bits or more than a byte. But this design that I'm talking about, each node indexes a 1 byte span from the tree. So the first node will index the first byte from the key. So let's think about a few 3-letter words. The name Bob, okay, Tom, right? And what about Bill? Okay. And how about Carl. Okay, that's enough names, I think, just to illustrate the concept. And so, the radix tree is going to index only a 1 byte span in each node. So the first node, the root node, is going to index the first byte or the first character of all the keys that are in the tree. So here we have like a B, there's a C, and there's a T, okay? And so then we go to the next one, okay? So then there's going to be each one of these is going to have a child node, okay? So we know we're going to need like 3 child nodes. So I'm just going to draw them here. Okay. And one over here. All right. And so B is going to go over here to this one. C is going to go to this one. And T is going to go to this one. Okay. And so now these nodes at the second tier, you could think, they're going to index the second byte or the second character from all of the words that are in the tree. So we have an I and an O after B, so I'm going to do an I and an O. And we have the C one, and there's only an A. Okay? And then we have a T, which has an O. Okay, so next we have the third, right? The third tier, and so the children of the second row, the third row, they're going to index the third character from all of these. Okay, so I'm going to start from the left. We have one over here that's coming off of this, and it's going to be an L, and then it ends up going down here to an L. Okay. And then we might have another, I'm going to draw triangles, okay, when we reach it's called a leaf node, okay? You can put something in there that you want. For example, you might want to store records about people or something. So that's a leaf node. Okay, so that's I-L-L. Then we have O, all right? So B-O-B, okay? And you get the concept. Each tier is kind of indexing only one character. C-A-R-L, okay? I don't even know if I need to finish this. I think you understand the concept. And one more here, M, okay? And so you can just keep doing this. And so I just wanted to, this is kind of just like a general concept of how a radix tree or a radix trie would work. Now, you can just keep on inserting things, and each node can index all of the different characters that could be at that. Each node can index all of the characters, or code points, you could think, or whatever, all of the numbers, right? If you think of like an ASCII table, each of these is like a number. Okay, you've seen these ASCII charts, all the letters and characters, and then the number behind them. And so each of these is like a number, and this is the general concept behind a radix tree. But if you think about how could you implement a radix tree, well, this is like the classic naive way of implementing this kind of a data structure. Okay, so let's imagine that you just have an array. Each node is actually just an array with 256 slots. Right? Why 256? Well, because a byte has 256 possible values. So you have all these indexes here. These are the slots that are numbered, right? Starting at 0, 3, 4, all the way up to 255. Okay. And a naive way is each one of these nodes is one of these arrays. And so if you insert a character, well, what do? You look up the number for the letter B, for example, and then you find that index, the number for that letter B. You find that slot in the array. Okay, so if the letter B is actually not number 3, but let's just pretend that it is, then this is where you would put your pointer or something, or reference to the next node, which is also one of these big arrays, okay? And so you can see this is like very easy to think about how you would implement, but the issue with it is that it uses way too much memory, right, to be useful. Because most of these arrays, most of these, like even this down here, right, there's only one character, but you still have 255 slots in this array just for one character. So it's very memory inefficient, and that's why we don't usually actually make tries this way. Well, the Radix tree, there is a famous paper called The Adaptive Radix Tree, Artful Indexing from Main Memory Databases by this um, computer scientist named Victor, I don't know if I'm pronouncing his name right, Reese. Anyways, I read this paper of his on how to make what's called an adaptive radix tree. And it's a tree that does all these things, but the nodes, they change size based on, or capacity, based on how much they need to store. So they're much more memory efficient. And I read that article and I read that in undergraduate and I was very, very excited, you know. I was so excited to try it myself because in computer science you learn about tries in undergraduate, but you don't really, you know, there's not really, at least in the undergraduate that there wasn't any serious discussion about how do you actually implement it, you know. When I read that paper, it was like, wow, this is a serious discussion about how you could actually implement it. And that's the key concept, is adaptively sized nodes. So I'm just going to explain to you what is his vision of adaptively sized nodes. Well, he envisions 4 different node types, okay? Starting with node 4, then the next biggest one, node 16, then node 48, and then node 256. Okay, and each of these numbers refers to how many keybytes it can index, or you could think of how many letters, right? So you can have up to, in node 4, you can have up to, it maps up to 4 different byte values to child nodes. This is up to 16, anywhere from 5 to 16. This one is anywhere from 17 to 48 byte values, unique byte values, and their children. And then this one is the biggest one, anywhere from 49 to 256 byte values to their children. And so this is a much more, you know, conservative in terms of memory, because, you know, the naive scheme here, where it's like 256 slots for every node, that's too much memory, right? But here, you're only using, you're being very conservative with how much you need, okay? So, you know, everyone starts out as node 4, and then, you know, once you have 4, and then you insert another byte in a node, and so now you need 5, well, then what happens is you create a new node 16. Okay, you copy all the values, the key bytes in their child nodes that they're mapped to, you copy all those things over to the new node 16 instance, and then you replace the node 4 with the new node 16. And you can do that you can migrate from node 16 to node 48 the same way, and, you know, from 48 to 256. And so basically, the same thing happens when you're removing things from a tree, okay? So say you have a node 48, and you keep on deleting stuff from your radix tree, and one of the node 48s gets down to, like, you know, 16 key byte values stored in it. Well, now that's kind of some wasted space, right? And so you just copy all the 16 values over to a new node 16 instance, and replace the node 48 reference with the new node 16. And so you're just, you know, migrating back and forth to the appropriate size based on the storage requirements. And this is a very effective way of managing, you know, memory, being more conservative with it. Each of these has the same set of, each of these different types has the same set of methods exposed for you to search for values and insert and remove things, and, you know, but how they're implemented differs. And so we're going to spend a little bit of time talking about, in the original vision of the adaptive radix tree that Victor wrote about, how does that work? Now, I actually, in my library, I ended up taking a slightly different approach with things. But before we talk about how mine is a little bit different, I want to make sure that you understand how each of these work. Okay? So first we're going to do node 4. So how does node 4 work? Well, ultimately, you know, it has to map each of these letters to its child node, right? So here's how it works for node 4. It's real easy. Okay, so you have a buffer with space for 4 byte values, okay? So 4 byte long buffer. Then you also have another array, Okay, I'm drawing a little bigger because the other array depends on what language. My library is in JavaScript, so I don't have pointers, I just have references, but you could be pointers or whatever. This is another array. This is a parallel array to this one. Here you would store the key byte values, okay? So you might have the key byte value of 42 stored in this one, and you might have 73 in this one, right? And maybe you only have 2 in here though, you know, because anywhere from 1 to anywhere up to 4 values, right? And then the child node that corresponds to 42, that's going to be stored right here, okay? So I'll just draw this an arrow, right? These indicate pointers or references like I do in JavaScript. And this one is going to be the reference to the child that corresponds to 70 key byte 73. Okay, so what happens is the key bytes are stored over here. They're always stored in sorted order. Okay, so if you need to insert value 50, you know, 55. Okay, you don't just put it on the end here. What you do is you overwrite the value in this slot, and then you bump this one up here. Okay, so you always keep these values in sorted order, and that means you have to always make sure that these are at the same index that their parent key byte is in this array. So there's a little bit of bookkeeping work, but as long as you stay organized, it's very easy. Because it's short, what that means is anytime you need to check, for example, if a key byte value is actually in this node, for example, if you need to check if 55 is in there, well, you just start searching. You do what's called a linear search. You start at the beginning. 55, nope. 55, yep, oh, it's in there. Okay, and so you just do a linear search. The same thing when you need to insert things. You're linear searching for the right place to put it and just keeping track of things appropriately. Okay, so that's how this one works. Now, node 16 works exactly the same way. Okay, except you just have 16 slots in each array, and you're not doing linear search. You're doing a binary search. And so how does binary search work? There's a million videos about that, but it's the phone book algorithm, right? You start in the middle, and you check is that greater or less than what I'm looking for. You know, if it's greater than what I'm looking for, then you go left, and you divide the left half of the array in 2, and you check, and you just keep dividing like that until you find what you're looking for, or you don't. And so it's the same thing, just on a bigger scale with bigger arrays, and you're using binary search. Okay? Node 48. Now, this one is a little bit complicated to consider compared to these ones. So what you have is 2 parallel arrays still. But this one is 256 bytes in size. Okay, 256. I'm going to write x256 so you know how long it really is. 256 bytes. And this one is for child references or child pointers. There are 48. Okay. And so how it works is, whatever number you're putting in here, say the number 59, okay? 59, actually let's do a simpler one. Number 3, okay? Number 3 will get stored at the third index, so 0, 1, 2, 3. So 3 will go here. Now what do you put there? Well, you put the index that you're storing the child reference in here. How do you decide where it goes in here? There's a lot of different ways. We're going to talk about that more. I went with a specific vision. Some people don't do that. Some people, they will just search for the first, starting from the beginning, they'll just search for the first 3 index. That's not what I do, but just imagine. So let's say that, you know, number 2 is the first one, the first free one, okay? Or sorry, number 1, so 0 and index 1. Let's say this is the first free one. Then what you'll do is you'll put a 1 here, okay? And then this refers to this is your reference or pointer to your child type, okay? There's some ambiguity here, isn't there? And that's where I started to get a little bit creative with how I implemented it, because they leave some implementation details to the imagination in the original adaptive Radix tree paper. So there's some problem solving to do there, some decision making. and I'll talk more about how I solved some of the ambiguity there. Okay, and then there is the node 256 type. It is just one 256 byte array. Okay, and it's kind of like this. Okay, except it's more like if this was 256. Okay, so you know, whatever the key byte value is. So if the key byte value is 7, then you're going to go to the 7th index, and that's where you're going to put your reference to your child node. Okay? So whatever the index, the value is of the key byte, that's the index value where the child is going to go. It's dead simple, and actually it's the same thing as the naive try implementation. Actually, there's also some ambiguity here, but nonetheless, that's how it works. So these are the 4 node types. The classic adaptive radix tree implementation. And there is some additional problem solving to do with these node types, because let's envision a situation like this. Okay, this is what you would call a one-way path, right? So this is a branching node and this is a branching node, but there are some one-way paths in here, right? Nodes that only, you know, there's only one place to go. You go here, there's an A, and the next character is an R, or it isn't, you know, so there's only one place to go. And then again, there's only one place to go. So there's one-way paths in here. This is not a one-way path, okay, because you have choices from this node. Some of these nodes, there are no choices, right? So here it's not so bad, because this is a trivial example, but some data, high cardinality data, really long strings, numbers even, you know, there's going to be a lot of one-way paths. They can get quite long, and if you envision what that means, it means every node in the one-way path is going to have a whole node 4. Okay, that whole thing up there for each one of these. And that's still not very optimal, right? So the adaptive radix tree paper has a few genius suggestions about how to further optimize. Okay, so I'm going to give a short summary. I don't want this video to be like the only authoritative vision of like your understanding of adaptive radix trees, because the original paper is legendary. You have to read it to really you know, get his full vision. But I'm just going to give a brief overview of these optimizations. So his idea is there are a few suggestions. You know, these aren't like mandatory, but just a few suggestions. So one thing is called lazy expansion. Okay, so it means that when you're inserting things, once you realize that you've started into a part where there's a one-way path, just don't create one. Okay, instead create the leaf node then and there. So for example, in this one, you insert Carl. Okay. There's a C here, that's fine. You get to the A, you realize you're starting on a one-way path. So instead of creating the one-way path, his idea is just create a leaf node right then and there. Okay? And then what you can do is several different things. But basically, there's the chance that when people are using the tree, or you're using the tree later, you might end up in the wrong place. So in the leaf node, you probably have to store a reference to the whole key. Okay, so maybe you have to store the whole word Carl in the leaf node, so you can verify when you get there that you got to the right place. Okay. Another suggestion would be maybe you don't have to store the whole thing. Maybe you could just do the one-way path compressed and stored in this thing. Okay, that's one suggestion. That's lazy expansion. There's also, I'm going to draw another one here. Okay, you can just imagine, here's a branching node, and we have this thing here. Okay, and let's say these are like leaf nodes. Okay, right away that we've reached, and here we have a one-way path. Okay, one-way path. Ooh, and then this one, instead of going to a leaf node, ooh, now we're going to a branching node. Okay, So he has a similar idea to path compression, or to lazy expansion for one-way paths that are internal. Okay, similar idea called path compression. So his idea is, instead of making that one-way path and just leaving it there as like node 4s, what you do is get rid of that, and instead you put this little kind of additional data, a little buffer or vector inside of your node type called a prefix vector or something like that, and it has the values. Let's say this is like a K and this is an A. Well, then you would have the value of the compressed in this little buffer of the prefix that was compressed from this one-way path. Okay, you just keep it in there, and so then when you're traversing, you just have to account for that you might have these buffers, right? So that's this idea of path compression. And another thing that he did was he suggests there's two versions of path compression. Okay, so his idea is there's this kind right here, which is what you might call lossless path compression, which means like you could just keep on, as long as this internal one-way path is how big this could be, and you'll have the whole thing in there. That's what you would call like maybe a lossless version of compression. And his vision was that, well, you could have lossy compression too, which means instead of actually putting the whole prefix in there, don't even put the prefix, don't even put that in there. Instead of putting the prefix, oh, I picked up the wrong one. Instead of putting the prefix, just put the size of the prefix, okay? 2 in this case. And then when we get down to eventually, at the leaf nodes, you have to do the same thing that we've discussed over here. You have to somehow put the value of the whole key in the leaf node so you can verify that you didn't take a wrong turn, is the way that he puts it. Okay? So that is the classic vision of the adaptive radix tree, and that way you can still have your smallest node type as a node 4, and you can still save a lot of space, even more space, right? Because these one-way paths, it doesn't matter. You're still going to have a conservative amount of memory used, and so this is a cool idea. Now, there's pros and cons to each of these optimizations, but he's giving you some flexible, choices. I have some thoughts about these ideas, and it really depends on what your values are. So, in the title of the original paper is this idea of a main memory database. So this is a database where, the tables, you might think of it in, it has maybe kind of you might think of it as having kind of a, so you think about like the use case of this, and well, what is the use case, right? I mean, sometimes you just want to index things, but really getting from the key to the leaf, right, or from the key to the value that's stored in the leaf nodes, the triangles, that's what you really want to do. And if you think about this with a main memory database, well, it's kind of getting at like this concept of indexing that is what you do in databases. You want to retrieve all of the tuples from a table that match a certain set of restrictions, and the index, for example, a data structure like this is a way for you to search for all of those tuples that meet those restrictions effectively. And so it depends on the types of queries that you're going to want to use in order to retrieve tuples. I would suggest thinking of it in terms of those values in order to decide which of these optimizations is right for your radix tree. So in a future video, I'm going to talk about what are the optimizations that I decided to make, the design choices that I decided to make in order to, the things that I wanted to support with it. So anyways, thank you for watching, Bye for now.